measure if the diameter of the cylinders has not changed. This is just a control that you want to do. In this case, you know that the image that you are looking for is a function which is either metal or air, so 0 or 1, for example. And you know that the shapes are just the circles. You are not going to make an image which is something else. You know that they are the circles. If you know that they are the circles, each circle can be defined by the position of the center, the ray, and probably if you know that inside the circle there may be air, there may be oil, there may be something else, you can also put the amplitudes here. So in this case, again, the problem becomes parametric shape. But this cannot be applied, for example, in medical imaging, where you are looking for a section of the body. You do not know. The shapes are no more the circles everywhere. You want to make really an image. Okay? So these parametric methods can be applied in very specific cases, not everywhere. And so the third category of the methods is the methods that we mentioned here. I can call it non-parametric, or I can call it algebraic methods. The main idea, again, the general case is that we are going to assume that f can be written, can be decomposed on a basis function. Okay? So the number of these basis functions in general must be really high to be able to do this approximation good. For example, the basis function here would be a function which is, the basis function here would be a function which is equal to 1 here and 0 elsewhere. In this case, the value of fj is the value of the mean value of the pixel j. Okay? But we know that n in this case must be very great, because the size of the pixels must be very slow, and the number of the pixels in general is very important. Okay? But this basis function bj can be a function which is like this, but can also be used other bases, Fourier basis, wavelet basis, spline wave basis, and so on. In general, can be any basis. Okay? But the simplest bases are, for example, the basis like this. So you are going to assume this. Put this expression here. The integral is here. You have this sum. Fj is here. H is here. B becomes here. And if you compute these integrals, which depend on the index I and the index j, you obtain hij. And if you note g of si as gi, you can see very easily that you obtain this expression. We put here the errors because there are errors here, and there are also the measurement errors, and this is the expression of hij. And then you can say, okay, this is not very different from the previous case. In the previous case, we wrote the expression of f as some finite number of the parameters. We did least square. Why we cannot do here the same? We can do exactly the same. Say, I am going to define the least square. F are actually the parameters. Why not? But the problem is that the number of these parameters is very huge. In the parametric case, in the previous parametric case, the number of the parameters was reduced. Here, the number of the parameters here is very important. Even if, so the name non-parametric does not mean that we cannot assume that this is not the parameters. Actually, they are the parameters. But it means that the number of these parameters are very important. So in general, the least square methods will not give satisfaction. Will not give satisfaction because even if you can minimize this function, the minimum of this function is when G is equal to HF, when G is equal to HF. And last day we showed that if the matrix H is ill-conditioned, which is the case always, this criterion will not give satisfactory results, and the results may depend on the initialization of the optimization algorithm, on the errors on the data, and so on. So it will be this least square solution will not give satisfaction. This is the discretization that I have showed you. The Bj is a function which is equal to 1 here and 0 elsewhere. Fj becomes the value of this pixel. Hij becomes the length of the ray number I in the pixel j, and we can write this expression. One advantage of this technique is that assume that in X-ray tomography we assume that there is a source of X-rays. You have the detector, and we assume that the rays goes in a straight line, and here the size of the detector we didn't account for. What happens if here the detector has a size which is not negligible? It means that actually the rays goes not on a line but on a strip. It is no more a line. All the strip here, so we have to compute this integration is no more over a line but over a strip. But in that case, in this case, it is not any problem to account for that. In analytical method, we couldn't, because Radon transform was the integration over a line, mathematically over a line. In this case, we couldn't use the Radon transform if we wanted to account for the width of the detector. But here we can take account for the width of the detector, and in that case, Hij will not be just the length of this trajectory, will be the surface of this band. And then we can again apply these algebraic methods. So in summary, whatever the application, linear or non-linear, you have F, which represents your unknown, G represents the data. In the linear case, this becomes a matrix vector operator. In the non-linear case, that may be anything. As I told you, one of the techniques which extrapolate the least square techniques, least square will be a particular case of this technique which is called data matching. Data matching, what is the main idea of data matching? The data matching is, I am going to define a distance between there are many different distances, between the observed data and the output of the model. Observed data, output of the model, a distance, And it is normal that we want to minimize the distance between the observation and the output of the mathematical model. What are the distances? L2 distance gives the least square. LP distance, where we put here power P in place of 2, P between 1 and 2. P equal to 1 says L1 distance, and P equal to is L2 distance. But there are many other distances. For example, Kullback-Leibler distance or divergence distance based on the entropy. And this is also a distance. Can you tell me, or can you remember what are the properties that a function has to have to be considered as a distance? Distance between x and y. What are the properties? First property is that delta of x and x is equal to 0. Delta of x and y is always positive if x is different of y. And what else? Distance of x and y is equal to distance of y and x. And you have also the Pythagorean relation, which is the distance between A, B, and C. The distance between A and B is always less than the distance, less than sum of the distance between A and C and B. Okay, these are the properties of any function distance. Here, these two expressions are really the distances. This expression satisfies all the properties except that it is not symmetric. This property is not given here, but it is possible to transform it to a symmetric case. This is not really a point that I am going to mention it. And but whatever the distances that we choose, what I have written here, whatever the distances that we choose, the results may be different. But if really we optimize these distances, optimizing these distances means that what? Means that G is equal to HF. And we saw before that G equal to HF, the exact solution is never good. We prefer to have approximate solutions which are less sensitive to the errors than the exact solution which is more sensitive to the errors. This is a point which is very important. So what to do in the inverse problems? The main idea is, the idea of regularization is that we have to add something else to this part. This part is necessary, it's important, but we need something else. We need some prior information. And you remember that we talked about least square, and we talked, for example, that we need to select one of the solutions which has energy minimal. We talked about generalization. So we need something else, prior information. And this prior information, one of the way to include this prior information is to add to this least square criteria something else. And this something else is called regularization term. And the parameter is called regularization parameter. Between the solutions that we have proposed before is this. This is the energy, which means that not only we are trying to minimize this, we are also trying to minimize this part. So we are trying to minimize this and at the same time the energy of the signal. To explain this expression of D here, let me go back to the examples of the convolution that we had before. Do you remember this exercise and this example that we mentioned? If you remember, I told that if the input is this, the output will be this. And I told you that if I put another input, which is this one, the corresponding output was again practically the same. So when we had this output and we wanted to solve the inverse problem, we didn't know which of these two solutions are present at the input. Do you remember that? Now, if you do not know which of the two solutions are present, which one do you prefer? Which one is more realistic? The one which is smoother. And the smoothness, so smoothness is something that very often we want to impose. So if I have this output, I would prefer, if my method wants to give me a solution, I would prefer to have a solution which is smoother, because this corresponds more to the reality. Because this, so how to impose this smoothness? How to impose this smoothness? How do you distinguish between two signals, one which is very rapid and another one which is more slow? You can look at the derivative and the energy of the derivative. If the energy of the derivative is low, means the signal is smoother. And so here, if I put here an operator of the derivative, this gives the energy of the derivative of the signal. And so trying to minimize this means that I am looking for a smoother solution. Okay? So this is a classical rigorization, and there is a book by Tikhonov. It's mathematical book, but he proposed exactly this smoothness prior, and not only here he put the derivative of order 1, but he proposed to use all the derivatives of the signal to impose the smoothness. But in summary, we put here something which translates what we are looking for, what is all prior information that we are looking for. And this is just this derivative operator here, and this energy imposes the smoothness. We can generalize this. And to say that this is a distance between G and the output of the model, and this one, for example, or this one, is also a kind of distance between, for example, here, I can write it f minus 0 power 2. So it is a distance between f and a solution which is just 0. Now, this can be interpreted as a distance between the solution and a solution which is just 0. So we can extend this to say that this is the distance between a solution and a priori solution, or the solution by default. Very often we can take it 0 because we do not know too much about the solution, but this is more general case. And then we try to optimize this. Optimizing this will give the good solution of the problem. So this is a good way to handle inverse problems. This regularization theory dates to 1940, I think, 50. So all the theory is very well done. There is a lot of works which has been done. Many of these regularization techniques has been applied, has been used in real practical applications, but still there are a lot of work to do. And in particular, how to choose delta 1 and delta 2. This is one of the questions that arise very often. Why did you choose L2 and not L1? Why did you choose this distance and not the other distances? This is one of the questions. The other question is that how to determine the regularization parameter. If you put lambda equal to 0, you will obtain a solution which is very erratic. If you put lambda equal to infinite, the solution does not depend on the data. If you put lambda equal to infinite, so it means that this term does not play any role. So the solution is always the same, no matter the observation. This is not good. And so how to find the right value of lambda, which is a compromise between data matching and the prior information. So these are the questions which still, there are some partial answers for that, but these are the questions which are still open. And as I mentioned here, actually, if you choose this distance, this means that you have assumed that the errors are Gaussian. I will show you this a little later. But there are some applications in which we know that the errors are not Gaussian. But so in this deterministic method, we cannot account for this kind of information. So my advice is to go to probabilistic method. And the probabilistic method, one of the advantages starting by is that we can account more specifically for the errors. We do not just say that they are errors and we do not want to know about. We are trying to account for the errors. We know that there are errors. We may know some information, but incomplete information about the errors, because the errors cannot be modeled really deterministically. We use probability theory to take account for the errors. So explicit account of the errors and noise. And we will see in particular that I am not going to explain all these methods. If I have worked myself for a long time on maximum entropy, but no, we are going just only to talk about Bayesian inference. So in the Bayesian inference, we will see that we will have, if you know that the solution is smooth, okay, regularization theory gives you the possibility to account for. But what if you know that the solution is not smooth, in the opposite direction? You know that the solution is spiky. How to account for that? You know that the solution is everywhere 0 and sometimes the peaks. How to account for that? You know that the solution is constant by piecewise constant. How to account for that? In deterministic way, it is not easy to account for this prior information that I mentioned. In probabilistic methods, in the Bayesian approach, it is possible to account for this information. And we will see that this Bayesian approach will give us a coherent approach